after, or final I should say, plus the momentum of the goalie finding. And this is conservation momentum. See, there's no change in momentum. What you have before in this isolated system is equal to what you have after. So that's why conservation of momentum is concerned. Now, to do this problem, it tells us that we have a mass, an initial velocity, and a mass of our hockey puck. PI, in other words, would be equal to MP times V, right?
Didelot, you keep moving the paper over.
Didelot, you keep moving the paper.
Wait, why is there a circle?
No.
This is the most confusing.
Okay.
Okay, look, this part right here is rewritten like this, because that's the velocity.
Yeah, it's fine. I'll
It's
just
initial, actually, right?
If I can figure out what he's writing.
Didelot, can you move it down just a little bit, please?
You're missing the top two pieces of information from the practice problem?
Does that say MPVP?
Yes. Yeah, mass of the puck times the initial velocity of the puck, okay, plus the mass of the goalie times the initial velocity of the goalie is what? They don't say it's moving, so we can just go ahead and cancel that out. 0 times his mass will be 0, so let's not worry about it.
Wait, what is that for?
Yeah, why do you cancel it?
Because
The velocity, the initial velocity of the goalie, they don't say he's charging the puck or going backwards, do they? You have to assume he is initial velocity.
It says he's at rest.
He's at rest. They say he's at rest. Thank you very much. I'm not reading the problem as I'm doing it. He's at rest. His initial velocity is 0, so this whole thing, since it's multiplied, goes to 0, and you don't worry about it anymore. You understand, Dietrich? Yes. What?
So
And guys, this is going to be harder than what you have on your test. So don't
wait, so Mr.
fall
Van,
into this.
just to confirm, to get the PI, what you're doing is multiplying the mass of the puck times the velocity given.
Well, yes, times the initial velocity given, which at first I didn't write was its initial velocity.
Okay.
Okay? Now, we know these two things. All right, they give them to us. On this side, let's look. The velocity of the puck final plus the velocity of the goalie final. Now that's going to be the mass of the puck final times the velocity of the puck final plus the mass of the goalie. Oops, that's a big L. No M, I'm sorry. Mass of the goalie final times the velocity of the goalie final. Now, if the goalie caught the puck, then his velocity is the same as the velocity final, right? Now, they both have their different masses, so on this side, we can collect those two like terms. But for the purposes of this, we're going to say the ice is pretty much frictionless. The goalie's way out ahead of maybe the goal when he catches the puck, so he has plenty of room to slide anyway. Okay?
Is it 3 points?
But if we're frictionless, he would keep sliding, and of course the puck and him would eventually go to the goal. So we got to ignore those kind of things. Anyway,
I got points.
what did you get, Laura? You got.
Oh, it's 6.1.
It's 6.105.
6.105 for.
No, it's
No, it's
0.105.
Yeah, it's 0.105.
That's why I got it different.
0.06. Yeah, that's what I got.
0.67 meters per second when you're around. That's
I've
correct.
seen it.
That is the final velocity. Obviously not very fast, but you expect the little cup was hot, hit a little hard. That goalie's massive, so when it hit him, he shouldn't go off looking too bad. Conservation of momentum. We're not going to consider any other kind of situation. What time is it, guys?
We have 7 minutes.
We have 7 minutes.
This is actually fun.
Is it real? Does anybody have any other questions on the homework? I want to remind you, because I didn't, not in this chapter, probably not. I think my test that I made out
I just noticed I didn't do much of the
generally, yes, unless, like I said, yes, unless for some reason you imagine.
Taylor.
Lots of
Hey, Felix.
something, but usually that's not.
How you doing?
Usually you just do that.